So let me move on and describe. So if this was perfectly inelastic, so not elastic, right? If that's not elastic, what does elastic look like? The truth is we can start right here. This is where we can start. So let me abbreviate what happens above and talk about elastic collisions. So here is A moving in really fast with a big velocity, v sub A. And here is B, which is still at rest because this is t equals to t start. This is the start of the collision. And what's interesting is this is the start of collision process, because you can see that it takes some time for the process to finish or to conclude, right? We could say that the conclusion has been met because the force has turned off. So this is the start of the collision process, and it goes, and B speeds up, and A slows down, and they have a common, somewhat smaller velocity, velocity A and B, right? They have the common velocity, and it's exactly the same as the previous case. Here we are at t sub m. But instead of the force profile turning off directly, because they have now reached a common velocity, elastic collisions aren't finished yet. So what happens is F on A by B, here's Ts, Tm. The force is 0 before the start of the collision. Now, during the beginning of the collision, the force climbs up and gets to some big value, and that's normally when, or that's when the inelastic collision finishes, but the elastic collision's not finished. The elastic collision gets to keep happening for some more time, and we could say that it happens until some t finish. And so I'm going to boost ahead and draw t finish. So this is the moment in time t finish, and we're going to take, because it's kind of interesting, the special case of the mass of A equals the mass of B. In the earlier situation, it just wasn't important. But in here, if we have the special case where the two objects have exactly the same mass, after t finish, we can have something really interesting. So t finish here, and so after t finish, so this is a time after t finish, the object B has all of the motion, so that's the velocity of B, and what's interesting is the object A is perfectly at rest. So object A came in really fast, hit object B, which was initially at rest. And during their exchange, right, this process occurs because the masses are the same. This is very special to this mass equals, or m and mass b are the same. That's very special to this. You'll end up with A standing completely still and B being the only thing moving after the collision is finished. What it looks like right at that moment in time when the force turns off is A, and actually I should draw A right here because that's where it's going to be at this moment in time. It has just come to rest, and B has finished picking up all the motion. This is the moment in time that the force finally does actually stop being non-zero. At a time that's in between. So let's say that t, we're checking a time that's after the max has happened, which is here, but before the finish has happened. All we have is A continuing to lose speed and B continuing to gain speed. All right, so very quickly though, or actually not quickly, I think this is important. So let's go back here in the inelastic collision. In the inelastic collision, if you look at this, B gained momentum. B gained momentum. Can you see B had no momentum? So you could say that the momentum of B equals the 0 here. It's still 0, but now can you see the momentum of B has grown? But A, because A's speed is decreasing, can you see that A's speed decreases from here to here, and then from this time to that time? A lost momentum. But in this inelastic situation, they both end up with momentum at the end. So B gained momentum up to some value, and A lost momentum down to some value. So B gained momentum, that means that there was a change in the momentum of B, and it is not 0. And the reason that we can see it's not 0 actually is this is the integral of the force on B by A through time. And the only times that there is a non-zero force are from Ts to Tm. So what we just calculated is the impulse, and look at this language, it's given to B by A. And that's because it is associated with the force on B by A. So this is the impulse given to B by A. Right? Okay, so this impulse is this area, right? This is J. J is the integral of F versus T. Here it is, integral of F over T. In this case over here, because we have more empty space, let's go and explore the fact that up until the inelastic, or the beginning of the collision has finished, can you see that that impulse is right here? But the thing about elastic collisions is they're not finished when the two objects reach the same speed, the common speed, so that they're moving together. In elastic collisions, the bounce of elastic collisions involves, so bounces involve large impulse. Not necessarily large force. Remember, impulse and force are different issues. The impulse is just the combination of a force getting to act over a time interval, right? So bounces involve kind of large impulses compared to inelastic situations where there's no bounce, right? They have a common velocity, and that's just the way it is for the rest of time, unless something else happens. Okay, so this is the force on B by A. So this is the impulse given to B by A if they have an elastic collision. But Newton's third law, remember I said I was going to get to the third law, it guarantees us something. It guarantees us that for every action there's an equal and opposite reaction. So this, we know, right, we have the force, oops, this is on, I'm so sorry, I did this, B by A, I switched it up, excuse me, this is supposed to be, right, the force on B by A So the force on B by A, if you take the opposite of it, you get the action. So for every action, there's an equal but opposite. Opposite means minus sign, reaction. But Newton's third law keeps the same objects. It's all within the single interaction. So this is the force on A by B. So over here, A pushes forwards on B, and B pushes backwards on A. So here's the backwards-forwards relationship. They have the same size. It's just exactly the opposite direction. So these are anti-parallel vectors. What's more, and this often doesn't get stated, Newton's third law is a happens at the same time kind of a law, because look, we have this force on B by A that's actually time dependent. So if this is time dependent, then so is this, and this is equal to the opposite of that at the same time. And that's important because what this means is if you look at the force profile for the force on A by B, it'll start at the same time, get the max value at the same time, and also finish at the same time. But it's always negative. And so this impulse here, this is the impulse given to A by B. This is the impulse given to B by A. It's this positive or topside area. This is the impulse given to A by B. It's this negative area because all the forces have a relative minus sign compared to those forces. But they're the same magnitude and happen at the same time. All the changes, all the details are just upside down.